Let's discuss Chapter 4, Advanced Containerization, Optimizing Runtimes for AI Workloads. Moving on to theoretical foundations. The deployment of scalable AI inference services within a cloud-native ecosystem represents a paradigm shift from monolithic model serving to distributed, resilient, and dynamically orchestrated microservices. This architectural evolution is driven by the computational intensity of modern AI models, the variability of inference workloads, and the stringent requirements for low latency, high throughput responses in production environments. Now, let's explore the containerization of AI agents, beyond simple packaging. Containerization of AI agents is not merely about wrapping a Python script in a Docker container. It involves a sophisticated orchestration of model artifacts, runtime dependencies, and inference engines optimized for specific hardware accelerators, GPUs/TPUs. In the context of .NET and C#, this process leverages the Microsoft.ML.OnnxRuntime or TorchSharp libraries to run models natively within the container, ensuring type safety and performance characteristics that align with the host application's lifecycle. The analogy of the modular factory: imagine a high-precision manufacturing plant. In a monolithic architecture, all machinery is bolted to a single concrete slab. If one machine overheats, the entire factory halts. In a containerized microservices architecture, each machine, AI agent, is placed in its own soundproof, climate-controlled booth, container. These booths can be rearranged, scaled, or replaced without stopping the production line. The booths share a standardized power and communication interface, Kubernetes services and ingress, allowing them to work in concert. C# and dependency isolation. In C#, the assembly load context, ALC, provides a mechanism for isolating dependencies within a single process. While containers isolate processes, ALCs isolate assemblies. This is critical when deploying AI agents that might rely on different versions of Newtonsoft, JSON or Microsoft.extensions.ai. The ALC acts as a logical container inside the physical container, Docker, allowing an agent to load a specific version of a library without conflicting with the host application or other agents. We begin by importing essential namespaces. System reflection is crucial for inspecting and manipulating assemblies at runtime, which is fundamental for dynamic plugin loading. System runtime loader is where the magic happens for custom assembly loading, allowing us to isolate dependencies. This isolation is a cornerstone for cloud-native applications, especially when dealing with multiple AI models that might have conflicting library versions. Without it, you'd quickly run into DLL hell issues, making your microservices fragile and difficult to scale. Here, we define our custom assembly load context named Model Agent Context. This class is the heart of our dynamic plugin loading mechanism. By inheriting from assembly load context, we gain control over how assemblies are resolved and loaded. The comment at line 4 explicitly states its purpose: loading a specific AI model's dependencies. This is a critical architectural decision for microservices that host multiple AI models. Each model can be treated as a plugin with its own isolated dependency graph, preventing conflicts and enabling hot swapping or versioning without affecting other models. Inside our model agent context, we declare a private read-only field, _resolver, of type assembly dependency resolver. This resolver, initialized in the constructor at line 11, is key to finding the correct assembly files on disk. The constructor takes a plugin path, which tells the resolver where to look for the plugin's assemblies and their dependencies. Notice the isCollectible, true parameter in the base constructor call at line 9. This is an extremely important detail for memory management in cloud-native environments. It means that once all references to assemblies loaded by this context are released, the context and its loaded assemblies can be garbage collected, freeing up memory. This is vital for long-running services that might load and unload different AI models over time, preventing memory leaks and ensuring efficient resource utilization in containers. The core logic for custom assembly loading resides in the overridden load method. When the .NET runtime needs to load an assembly and it's not found in the default context, it delegates to our custom context's load method. At line 16, we use our _resolver to attempt to find the full path to the requested assembly name. If a path is found, line 17, we then explicitly load the assembly from that path using load_from_assembly_path at line 19. This ensures that the assembly is loaded into this specific model agent context, isolating it from other contexts. If the resolver can't find the assembly, we return null, allowing the runtime to potentially try other contexts or fail. This controlled loading process is fundamental for maintaining dependency isolation, a key principle for robust and scalable microservices. Optimized runtimes and ONNX. The Open Neural Network Exchange, ONNX, format is the lingua franca of model deployment. By converting models from PyTorch or TensorFlow to ONNX, we decouple the training framework from the inference runtime. In C#, ONNX.Runtime provides a high-performance execution engine. When containerizing, the Docker file must install the specific GPU-enabled ONNX runtime NuGet package, Microsoft.ML.OnnxRuntime, GPU. This ensures the container image is lean, containing only the necessary binaries to execute the model on the available hardware. Now, let's explore Kubernetes, the orchestrator of inference workloads. Kubernetes, is the control plane for our distributed AI agents. It abstracts the underlying hardware, allowing us to define desired states for our inference services. GPU resource management, standard CPU scheduling is insufficient for AI workloads. Kubernetes uses extended resources to manage scarce hardware like NVIDIA GPUs. When a pod requests a GPU, the Kubernetes scheduler ensures it lands on a node with an available GPU device. In C#, we interact with these resources via environment variables injected by the Kubernetes device plugins, e.g., NVIDIA_visible_devices, which the ONNX.Runtime automatically detects to allocate compute kernels. The analogy of the air traffic control tower, Kubernetes acts as an air traffic control tower for incoming inference requests, planes. It doesn't care about the specific model inside the container, the plane's cargo, it only cares about the weight, GPU memory, destination, node affinity, and traffic volume, autoscaling. If the runway, node, is full, it redirects planes to a holding pattern, pending state, or spins up a new runway, cluster autoscaler. Autoscaling strategies. 1. Horizontal pod autoscaler, HPA scales the number of replica pods based on CPU/memory utilization. 2. CADA, Kubernetes event-driven autoscaling scales based on external metrics, such as the length of a message queue, e.g., RabbitMQ or Azure Service Bus, holding inference requests. This is superior for bursty AI workloads. 3. Vertical pod autoscaler, VPA adjusts the CPU/memory requests of existing pods, less common for stateless inference, but useful for heavy batch processing. Let's discuss service meshes, the nervous system of interagent communication. As AI agents become more complex, they rarely act in isolation. A request might flow from an API gateway to a pre-processing agent, then to a model inference agent, and finally to a post-processing agent. A service mesh, like Istio or Linkerd, manages this traffic. Why a service mesh? Without a mesh, the application code must handle service discovery, retries, and circuit breaking. This bloats the C# code and couples agents to specific network topologies. A service mesh offloads these concerns to the infrastructure layer using sidecar proxies, e.g., Envoy, injected alongside each pod. The analogy of the postal service, imagine sending a package, inference request. Without a mesh, you must know the exact address of the recipient, drive it there yourself, and if the recipient isn't home, you must drive back and try again. With a mesh, you drop the package at a local post office, sidecar proxy. The post office handles the routing, ensures it reaches the correct sorting facility, service A, and forwards it to the final destination, service B. If the destination is unreachable, the post office holds it and retries automatically. MTLS and security. In AI deployments, data privacy is paramount. A service mesh automatically enforces mutual TLS, MTLS, between pods. This ensures that the data passed between the pre-processing agent and the inference agent is encrypted, even within the same cluster. Let's discuss performance optimization for distributed inference. Distributing inference introduces network latency. Optimizing this requires specific architectural patterns. Batching versus streaming, static batching, grouping multiple requests into a single tensor to maximize GPU utilization. This is done at the inference service level. Dynamic batching, middleware, like NVIDIA Triton Inference Server, automatically batches requests arriving within a small time window. In C#, we can implement a simple batching queue using system, threading, channels or blocking collection T to aggregate requests before sending them to the model. The analogy of the bus system, static batching is like a scheduled bus that waits until it is full before departing, high efficiency, higher latency for the last passenger. Dynamic batching is like a shuttle that departs every 5 minutes, picking up everyone waiting at the stop, balance of efficiency and latency. Quantization and pruning. Before deployment, models are often quantized, reducing precision from FP32 to INT8, to reduce memory footprint and increase speed. In C#, this is handled transparently by the runtime, but the container must be built with the appropriate execution providers, e.g., CUDA execution provider for GPU acceleration. Moving on to CI/CD pipelines for continuous model updates. AI models are not static, they degrade over time, data drift, and are retrained frequently. A robust CI/CD pipeline is essential. The GitOps approach, we treat the model artifact, ONNX file, and the Kubernetes manifests, YAML, as code. 1. Build stage. The pipeline converts a trained PyTorch model to ONNX, runs unit tests on the inference logic, using XUnit, and builds the Docker image. 2. Test stage. Deploy to a staging namespace. Run canary tests where a small percentage of live traffic is routed to the new model version to check for performance regressions. 3. Deploy stage. Update the Kubernetes deployment manifest. The Kubernetes controller detects the change and performs a rolling update, ensuring zero downtime. Feature flags in C#. To manage risk, we can use feature flags, e.g., via Microsoft.FeatureManagement, to toggle between model versions or algorithms without redeploying the container. At line 1, we import Microsoft.FeatureManagement. This is a crucial dependency for implementing feature flags, a powerful cloud-native pattern. Feature flags, also known as feature toggles, allow us to dynamically enable or disable features in a running application without redeploying code. This is incredibly valuable in microservices architectures, as it facilitates A/B testing, canary releases, and emergency kill switches for new functionalities or models, ensuring high availability and controlled rollouts. Observe lines 3 to 8, where we define the inference service class and its private read-only fields. This service is designed to encapsulate the logic for performing AI inference. We instantiate iFeatureManager, which will be used to check feature flag states, and two iModelRunner instances, _v1runner and _v2runner. The use of iModelRunner as an interface, rather than concrete classes, promotes loose coupling and adheres to the dependency inversion principle, making the service more flexible and testable. It means we can easily swap out different model implementations without altering the inference service itself. Look at lines 9 to 16, which define the constructor for inference service. Here, we're using constructor injection to provide the dependencies, iFeatureManager, v1 ModelRunner, and v2 ModelRunner. This is a best practice in modern .NET development and aligns perfectly with cloud-native principles. By injecting dependencies, we make the inference service stateless and independent of how these dependencies are created. This statelessness is vital for horizontal scaling in cloud environments, as any instance of inference service can handle any request without relying on internal state built up during its lifetime, allowing Kubernetes or other orchestrators to freely scale it up or down. At line 18, we define the public asynchronous method predictAsync, which takes input data and returns an inference result. The async task return type indicates that this operation is potentially long-running and non-blocking, which is typical for AI inference tasks, especially when dealing with large models or network latency. This asynchronous pattern is crucial for maintaining responsiveness in a microservice, preventing thread exhaustion, and allowing the service to handle more concurrent requests efficiently, which is a key performance characteristic in cloud deployments. Notice lines 20 to 22. Here, the core logic of feature flagging is demonstrated. We call _FeatureManager.isEnabledAsync, v2 model enabled, to determine which model runner to use. This is a powerful technique for A/B testing or canary releasing new AI models. For example, we could configure the v2 model enabled flag to be true for 10% of users, or for users with a specific ID. This allows us to gradually roll out a new, potentially more performant or accurate, AI model, v2, to a subset of traffic, observe its behavior in a production environment, and quickly revert to the older model, v1, if issues arise, all without code deployment. This significantly reduces deployment risk and enables continuous delivery. If the v2 model-enabled feature flag is active, line 21, then at line 23 to 24, the _v2runner.executeAsync input method is invoked. This means the request will be processed by the newer, potentially more advanced or resource-intensive, AI model. The ability to switch between model versions dynamically like this is essential for MLOps practices, allowing for seamless model updates and experimentation. In a cloud environment, the v2 model runner might be backed by a different set of compute resources, e.g., more powerful GPUs, and feature flagging enables us to control when those resources are engaged, optimizing cost and performance. Finally, at lines 25 to 27, if the v2 model-enabled feature flag is not active, the system falls back to using _v1runner.executeAsync input. This ensures that there's always a stable, known good model to serve requests. This fallback mechanism is critical for reliability and resilience in a production system. It's a fundamental aspect of graceful degradation and ensures that even if the new model has issues or is not yet ready for full production traffic, the service can continue to provide inference results using the established model. This pattern contributes to the overall robustness required for cloud-native applications. Now, let's talk about theoretical foundations. Why introduce Kubernetes, service meshes, and complex CI/CD for AI? The answer lies in the non-functional requirements, NFRs, of enterprise AI. 1. Latency versus throughput trade-off. A monolithic Python script might be fast for a single user but fails under load. By containerizing and scaling horizontally, we sacrifice a tiny amount of overhead, container startup, for massive horizontal throughput. 2. Resource fragmentation. Without orchestration, a powerful GPU might sit idle while a CPU-bound service is overloaded. Kubernetes bin packing ensures that inference pods are co-located with appropriate resources. 3. Observability. In a distributed system, a request might fail at the network layer, the serialization layer, or the model execution layer. C# integrates seamlessly with OpenTelemetry, exporting traces and metrics, Prometheus, that are aggregated centrally. This allows us to pinpoint if a slowdown is due to the model inference, GPU bound, or the network hop, IO bound. Now, let's explore conclusion. The theoretical foundation of cloud-native AI rests on the principle of decoupling. We decouple the model from the training framework, via ONNX, the compute from the hardware, via Kubernetes, and the network logic from the business logic, via service meshes. C# serves as the robust, type-safe glue that binds these components, offering high-performance execution and modern language features, like iasync enumerable for streaming responses, that are essential for handling the asynchronous nature of distributed inference. This architecture transforms AI from a static, brittle monolith into a living, breathing system capable of adapting to real-world demands. Let's discuss basic code example. We begin by importing necessary namespaces. Notice at lines 1 to 8, we're bringing in core C# functionalities like system for basic types, system, collections, generic for data structures like dictionary, system, link for query operations, system.net, HTTP and system.net, HTTP, JSON for HTTP client operations and JSON serialization, and system, text, JSON for more advanced JSON handling. At lines 9 to 11, we import Microsoft, extensions. Dependency injection, Microsoft, extensions, hosting, and Microsoft, extensions, logging. These are crucial for building modern .NET applications, especially microservices, as they provide the framework for dependency injection, background services, and robust logging, which are foundational for cloud-native patterns like observability and maintainability. At line 13, we declare our namespace, Cloud Native AI Microservices, example, which helps organize our code and prevent naming conflicts. Then, at lines 15 to 24, we define a C# record called inference request. This record type is a concise way to declare immutable data structures. It represents the input payload for our AI inference service. Notice how it includes a request ID, crucial for tracing and debugging in distributed systems, input data, the actual data for the AI model, and parameters, a flexible dictionary for model-specific settings like temperature or top_k. This design promotes a stateless approach, where each request is self-contained, which is vital for horizontal scaling in cloud environments. Following the inference request, at lines 26 to 34, we define another record, inference response. This structure encapsulates the output from our AI model. It mirrors the request ID for correlation, provides the result of the inference, includes inference time ms, essential for performance monitoring and latency analysis in a microservice, and model version. The model version is particularly important in cloud-native AI systems for A/B testing, canary deployments, and ensuring reproducibility or debugging issues tied to specific model iterations. Both inference request and inference response are designed for clear, self-describing communication between services, aligning with API-first design principles. At lines 36 to 43, we introduce iInference service, an interface that defines the contract for our AI inference functionality. This is a critical architectural decision. By abstracting the inference logic behind an interface, we achieve loose coupling. This means we can easily swap out different implementations, for example, a mock inference service for testing, a CPU inference service running on local hardware, or a GPU inference service leveraging specialized accelerators. This flexibility is paramount in cloud-native development, allowing us to adapt to different deployment targets, optimize for cost or performance, and facilitate independent development and deployment of components. Now, let's look at mock inference service from lines 45 to 58. This class is an implementation of our iInference service interface. Its purpose is to simulate the behavior of a real AI model without the overhead of actual model loading or complex computations. Notice the constructor at lines 55 to 58, where it takes an iLogger mock inference service as a dependency. This demonstrates the use of dependency injection for logging, a best practice for observability in microservices. Logging is crucial for understanding application behavior, debugging issues, and monitoring health in a distributed system, especially when deployed to containers where direct access can be limited. Within the mock inference service, at lines 60 to 70, we implement the predict async method. Observe at line 62 how we log the start of processing, including the request ID and input data. This is vital for tracing individual requests through the system. At line 65, we simulate inference latency using task delay. This delay, between 50 milliseconds and 200 milliseconds, is representative of the time a real AI model, like a smaller BERT or GPT variant, might take to process an input, especially on a GPU. Simulating this helps us understand the performance characteristics and potential bottlenecks of our system before integrating a complex, real model. Line 69 simulates a simple transformation, representing the computation of the AI model. Continuing in predict async, at lines 71 to 79, we log the completion of the request, again including the request ID and the simulated time. This allows us to measure the inference time for each request, a key performance indicator. Finally, we construct and return an inference response. Notice how we populate inference time ms with the simulated delay and set model version to v1.0 Mach. This comprehensive response provides valuable telemetry, enabling us to monitor the service's performance and ensure that the AI model is operating as expected. This data is critical for monitoring dashboards and alerting in a production cloud environment. Next, we introduce Request Simulator Service at lines 81 to 96. This class inherits from Background Service, a feature of the .NET generic host. Background services are perfect for long-running, non-HTTP tasks within a microservice, like processing queues or, in this case, simulating incoming requests. In a real cloud-native deployment, this background service would typically be replaced by an HTTP API endpoint, e.g., an ASP.NET Core Minimal API, exposed via an ingress controller in Kubernetes. The constructor at lines 93 to 96 again demonstrates dependency injection, receiving inference service and ilogger, ensuring our simulator can interact with the inference logic and log its activities. The core logic of our request simulator service resides in the execute async method, starting at line 98. This method is called when the host starts. At line 100, we log that the simulator has started. Then, at lines 102 to 104, we introduce a task, delay, 3000, stopping token. This initial delay is a common pattern in microservices to give other services or the application infrastructure time to fully initialize before the service starts its main workload. This prevents race conditions or errors that might occur if a service tries to interact with a dependency that isn't yet ready, especially in dynamic containerized environments. Inside execute async, from lines 105 to 118, we enter a while loop that continues as long as the application isn't being shut down, stopping token.is cancellation requested. This loop continuously simulates incoming requests. At lines 111 to 117, we construct a new inference request with a unique request ID and some mock input data. This simulation helps us test the inference service under continuous load, which is crucial for understanding its performance characteristics and resource consumption in a containerized environment. The stopping token is essential for graceful shutdown, allowing the service to complete any ongoing work before terminating, which is a key cloud-native best practice. Continuing in the while loop, at line 119, we make an asynchronous call to _inference service.predict async. This simulates the actual invocation of our AI model. The _ syntax indicates that we're intentionally ignoring the return value here, as the simulator's primary job is to generate requests, not necessarily process their responses. At line 122, await task, delay, 2000, stopping token, simulates an incoming traffic rate, sending one request every 2 seconds. This allows us to control the load on our mock inference service. The try-catch block, lines 125 to 133, handles potential operation cancelled exception during shutdown and logs any other exceptions, ensuring the background service is resilient and provides visibility into errors. At lines 136 to 147, we arrive at the program class, containing the main method, which serves as the entry point of our application. This main method is asynchronous, async task main, because it will be running background services. The host.createDefaultBuilder, args, call is the cornerstone of modern .NET microservices. It sets up a generic host that provides essential infrastructure like configuration, logging, and dependency injection. This pattern is highly recommended for cloud-native applications because it decouples application logic from hosting concerns, making it easier to deploy to various environments like containers or serverless functions. Inside main, at lines 148 to 155, we use configure services to set up our application's dependency injection container. Notice services.add singleton inference service, mock inference service. Registering inference service as a singleton is a deliberate architectural choice, especially relevant for AI models. In a real scenario, an AI model, like a large language model or image classification model, can be gigabytes in size. Loading it into memory is a costly, time-consuming operation. By registering it as a singleton, we ensure that the model is loaded only once when the application starts and reused for all subsequent requests. This dramatically reduces startup time and memory footprint per request, which is critical for efficient container resource management and horizontal scaling. If it were scoped or transient, the model might be reloaded for each request or user session, leading to prohibitive latency and memory consumption. Continuing the configure services method, at lines 156 to 161, we register our request simulator service using services.add hosted service to request simulator service. This tells the .NET generic host to manage the lifecycle of our simulator. It will start it when the application begins and stop it gracefully when the application shuts down. This pattern is excellent for background tasks that need to run continuously alongside the main application. Remember, in a production cloud environment, this simulator would typically be removed, and real traffic would come from external sources, hitting an actual HTTP endpoint. This demonstrates how the generic host allows us to easily swap out components for different environments. Finally, at lines 162 to 170, we configure logging and build and run our host. Configure logging, lines 162 to 166, clears default providers and adds @console, directing logs to the console. Setting minimum level to information ensures we see relevant operational details. This is crucial for observability in containers, where console logs are often captured by logging agents, like Fluent, and sent to centralized logging systems, like Elasticsearch or Loki. Build then constructs the iHost instance. The climactic call await host.runAsync starts the application, including all registered background services. This method blocks until the application is gracefully shut down, allowing our simulator to run continuously and demonstrate the inference service in action. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 4 of the C# and AI Masterclass ebook series and from the volume Cloud Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here, https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.